Welcome to our 1 p.m. press conference. This is again on the 11th March 2011 Japan tsunami. This is our second press conference on this topic. And we have 4 speakers who are going to speak in the following order. Kazuhisa Goto, he's a research associate in planetary exploration research, Chiba Institute of Technology in Narashino, Japan, and Tohoku University in Sendai, Japan. And I just want to mention that Dr. Goto, he's going to have to leave at 1:30, and he'll be convening a session in room 3010 up the hall. He'll be there all afternoon, so if you have questions about his talk, you can try to find him there. Our second speaker will be Tony Song. He's a research scientist at the California Institute of Technology Jet Propulsion Laboratory in Pasadena. Our third speaker is Patrick Lynett. He's an associate professor at the Department of Civil and Environmental Engineering at the University of Southern California in Los Angeles. And our final speaker will be Kostas Sinolakis. He's a professor at the Hellenic Center of Marine Research, Anavisos, Athens, Greece, and Department of Civil and Environmental Engineering at USC in Los Angeles. Oh, and I also want to mention one thing. For anyone who's following us through the web stream, you can see uploaded files. We're going to be uploading a file from this shortly, but there's uploaded files on your screen. Look in the folders there under Monday. And also, there's for all the reporters, there's a virtual press room site that AGU started this year, which is if you click on Media Center on the fall meeting website and look for virtual, it says virtual newsroom, but we are posting press releases up there. So let's go, we can go now.
Okay, so I start to talk about beach recovery, and I'm a geologist and working on tsunami sedimentology in the Sendai Plain. And not only the beach recovery, but also probably you are interested in the relation between the 2011 event and also in the past event called 869 Jogan tsunami event. So I will talk about the relationship about that. So major objective of the parallel tsunami research are estimation of the long-term tsunami recurrence interval and estimation of the inundation area, flow height, and magnitude of the earthquake for the tsunami risk assessment. And tsunami can transport offshore sediment to inland, and then it's deposited as a tsunami deposit like a sand seed, so we can identify its evidence of the past tsunami. And in Sendai Plain, it is well known that the occurrence of low-frequency large tsunami in the past, even before the 2011 tsunami event, and it called 869 Jogan tsunami event. And if you take a drilling core at the Sendai Plain, now you can get this kind of type of the core, and 2011 tsunami sand here, and Jogan tsunami sand is here. So this figure shows survey points before the 2011 tsunami event, and Jogan tsunami was very well studied before the tsunami, and the survey point was about 600. And according to the historical document, it occurred on July 13. And because of the extensive geological research, it was already known that tsunami recurrence interval is about 600 to 1,300 years, and tsunami inundated at least 3 to 4 kilometers from the parallel shoreline, and magnitude of the earthquake was estimated as more than 8.4. And this is kind of the animation that shows the modeling of the Jogan tsunami event. And this is a parallel topography, and this is a pit of the sediment layers. And this red line is the limit of the sand layers. And we did numerical modeling and tried to explain the inundation limit line. So tsunami wave at least reached to this red line. So, but it should be noted that the distribution of the sandy tsunami deposit implies a minimum inundation distance. So, the estimated magnitude might be underestimated. But at least doing this modeling, we found that magnitude 8.4 or something is enough to explain the Jogan tsunami deposit. And then we did a field survey for 2011 tsunami deposit, and we totally studied about over 300 sites. And this is a typical tsunami deposit in the rice paddy close to the beach. And actually, the beach recovery at the Sendai Plain is very fast. And this is before the tsunami beach satellite image, and this is 3 days after, and this is 13 days after, and the beach was already start recovering. And this also shows a cross-sectional profile, and this black solid line is a pre-tsunami topographic profile at the beach, and this gray line is a post-tsunami line. So this beach berm was eroded, but just 2 or 3 months later, it was recovered. And then this is a bit complicated figure, but this is a topography. And also, this is a flow height. So in the Sendai Plain, the topography is quite flat. So that's the reason why tsunami inundated far inland of about 4 kilometers or something. And this is a sand layer thickness change. And this circle shows the Jogan tsunami sand measured from the parallel shoreline. So it's quite similar distribution. So our tentative conclusion is that sedimentary features and sediment distribution area of the 2011 tsunami deposit are very similar to those of the 869 Jogan tsunami deposit. Although still we hesitate to conclude that the 2011 event is a recurrence of the Jogan tsunami, but it's quite difficult to find the difference between these two tsunami deposits. And also, we have an important implication to the paleo tsunami research, and is inundation distance of the Jogan tsunami might be underestimated significantly. It's quite important for tsunami risk assessment. So that's the reason why we taken care only the recognizable sandy tsunami deposit, and especially such a very thin sand layer is quite difficult to recognize in the geologic record. So future study should be done more carefully to understand the magnitude and recurrence interval also of the paleo tsunami deposit. Thank you very much.
Okay, my name is Tony Song. Today I will show you the evidence from satellite that confirms the long hypothesized merging tsunamis that can travel long distances and without losing its power. You can see the first I show these two satellite observations. They already see one of the satellites see the tsunami high is double another one. Even the two satellites see the same front of the tsunami. So first of all, let me introduce my collaborators. Ichiro Fukumori from the NASA Jet Propulsion Laboratory, also the Yunchang Yi and C.K. Xiang from Ohio State University. So Professor C.K. Xiang is in the audience, so later on if you have a question, he can help me on that. So we know that tsunami often destroy some coastal areas while leave some other areas without damages. So that's unpredictable tsunami behavior, complicated tsunami forecast. Here I show one figure is a model simulation of the 2006 Tonga tsunami. That's from Tong et al., published in 2008, showing specifically how the tsunami forecast is challenging. There's two actually specifically challenging. First is a near field forecast. We know the location, for example, here, but we have to forecast earlier. So that's a challenge in timing and the tsunami strength. Another challenge is a far field forecast. For the far field, you can see there's only few locations the tsunami can hit, but we want to know exactly where the tsunami is going to hit. So that is going to be challenging because you don't want evacuate everywhere along the coast. The large scale evacuation can be very costly. So this talk is about the far field forecast. So the question is, what is emerging tsunamis? Study in 1960, the Chilean tsunami that's generated by the earthquake is one of the largest earthquakes ever recorded. That's a magnitude 9.5. That tsunami crossed the ocean and killed more than 100 people in Japan and also many people in Hawaii. So since then, people is suspect the tsunami can merge the energy and focus on certain location and the direction, then can cross the ocean without losing its power. So here that's a model simulation originated from Woods and O'Connor. They show that such a thing can happen from their theory and the model. In this 2011 Japanese tsunami, all model all show a similar the tsunami jets or emerging tsunami cross the ocean. So that's also model result. Both models show that, or there's many other studies also show that. But whether this is true or not, so observation is lacking since or before. But here, we will use this methodology to prove such emerging tsunami exists. First, we use GPS data from Japan that's more than 1,200 stations to generate a tsunami source. Then we use a three-dimensional ocean model to simulate the tsunami. Then we match the model simulation by the satellite observation. Here is a movie to show how we match the model with satellite observation. See, there's a satellite track. You see that is seeing that, let me play once again. You can see the satellite only see the front, only at a certain location, they can see the emerging tsunami phenomena. Here is a snapshot of the three satellites seeing the tsunami front, the same tsunami front. Here the black one are the model predicted tsunami. The color are the satellite observations along the satellite track. You can see that only this one satellite called GS1 at the right place at the right time sees the merging point. At the merging point, the tsunami high is double another two satellites seeing the normal tsunami. The question is what caused this merging tsunami is known from theory and model. If we see this is the maximum tsunami, if we overlap this maximum tsunami high over the topography, here shown the color of the topography, here is the scale of the topography. You can see this jet or merging tsunami is initiated from the topography features. The one observed by the satellite actually is the mid-Pacific mountain. Initially from there, then the tsunami front merged and double its height and continue travel for long distances. That's seen by the satellite. So that's total Y. In summary, so for the first time, satellite observations clearly confirm the existence of this emerging tsunami over the ocean. By the way, satellite has been seeing tsunami several times. In the 2004 Indian Ocean tsunami, and last year the Chile tsunami, but none of them see the merging tsunami. So that's the killer waves across the ocean. So that's the thing we want to confirm. So by knowing this, we know where the tsunami can form this double high. Then we know how to predict the tsunami for the far field because we know the location of the earthquake. Then we know the topography from a deep ocean. Then we can map the high map. Also, we can better design the coastal facilities. Thank you.
Hi, I'm Pat Lynette from USC. I was fortunate enough to get to go on a Galapagos field survey. In fact, I got to go there twice to do a tsunami field survey, and I'd just like to talk about some of the things we found when we got to go. These two images give you an idea of the range of what you have in the Galapagos Islands. It's a very natural, rugged area, so there's lots of fresh lava plains, and you can see the sediment deposits on it that were brought by the overrunning tsunami. You also have small ports and small port towns where very close to the water, and you had some damage in these areas. In case you're not quite familiar about where the Galapagos Islands are, so they're just off the coast of Ecuador, more or less on the equator. So what you can see when you look at this, and this is just a simple map superimposed on the NOAA energy chart, there are no fingers of energy, these refractive focusings, going towards the Galapagos Islands. So if you were just to look at this map, you wouldn't necessarily expect that the tsunami would be particularly large in the Galapagos. But in fact it was. So this is the main area of the Galapagos Islands. You have 3 main islands. The island of Isabel right here, which is a very young volcanic island, the island of Santa Cruz, which is the main island with the largest city, and the island of San Cristobal on that side. And what you'll see is that these islands sit on a platform of relatively shallow water. And whenever you talk about tsunamis approaching the coast, approaching shallow water, the exact pattern of this shallow platform really controls how large the wave height can get. So what you could expect if you knew a little bit about tsunamis, in areas where it gets deep very quickly, wave height not so great. In areas where you have a relatively long shallow shelf, in cases like this, the wave height might be a little bit larger. All right, so the initial tsunami waves arrive in the islands at 5:30 in the p.m. They persist for many hours. In some places you had waves lasting for 20 hours or more. The low-lying areas and port towns were evacuated. The ships in the harbor were told to leave port, and there was no entry. The largest waves were among the first 3 crests, so this is a little bit different from what we found in places like in California, where the largest waves maybe happened 8 hours after the first wave. And this was of particular importance here in the Galapagos because those first waves arrived literally right at high tide. Okay, so the largest wave occurred within about 3 minutes of the highest of the high tide. So it was particularly poor timing for the largest waves to arrive in the Galapagos. You had widespread minor to moderate flooding, widespread 3 to 4 meter run-up. The largest run-up we found on the island is about 6 meters. Galapagos is a challenging place to do a survey. You have very challenging, rugged coastlines. There's little overland transportation just because there aren't towns, so there's no reason to have roads. You have very restricted access. The entire island chain is a national park. And you have a large spring tide 5 days after the tsunami, which helped to wipe out a lot of the tsunami signs. All right, so beach access is highly restricted and controlled by the Galapagos National Park. Typically, if you're a researcher, you go to the Galapagos, you apply for a permit, 30 days or so later and $1,000, they give you access to a particular beach. So we were able to go to the park and say, more or less, hey, a lot of these beaches were already damaged. By letting us go onto the beaches in a rapid response, we're not going to cause any more human interference, right? These are already affected areas. And so they went with that. They recognized the fact that this really needed to be documented. Galapagos is in a very seismically active area. They're going to be prone to tsunamis. They really need to have a better understanding of what the tsunami hazard is. In the Galapagos, you had very large stretches of lava coastline. So you imagine this black lava rock coming right up to the beach. So you're not going to land a boat there. You're not going to be able to find too many signs of what a tsunami is. But every now and then you'd get these pocket beaches of 100 meters or so where if you were lucky enough, there wasn't coral rock on the beach and you could land a beach and you could get off the boat onto the sand without cutting yourself open. Young lava rock is very sharp and jagged. In places, this is a good tsunami sign, and some of the young islands in the Galapagos. So you have a rack line, you can see that the sediment is a little bit different color from the sediment behind it. So the wave came in and it moved the sediment around. And so this is a type of sign that you might expect to see in parts of the Galapagos Island of a tsunami inundation. Where you did have sandy beaches, the area is characterized by relatively low wave energy. So you don't have very high dunes. You have relatively low dunes and relatively short beaches. So this is a good example of a beach, small dune. On top of the dunes, in almost all locations, you had sea turtle nests. So you see this little divot. What the sea turtles do, they come in, they dig a hole, they lay their eggs, they bury it back up. So what happens is, in a lot of these places, in most places, these dunes are overtopped. As soon as they're overtopped, the salt water percolates down and it drowns the nest. So you had a lot of issues where you had sea turtle habitat nesting that was destroyed and damaged by the tsunami. That didn't stop the sea turtles. We came back a week and 3 weeks after the tsunami, and they had completely reworked the dune crest and recreated nests. In some places, the dunes were breached and washed away. So this is basically a cross-section of a dune. So the dune would stretch along the beach. The wave cut through, and so you have this really steep erosion scarp. A lot of sediment had moved. In these areas, you could look into the side of the dune, and this is what you would see. So that's a sea turtle egg, which was pulled out and destroyed by the tsunami. So there was some habitat loss there, and this is another type of sign of a habitat loss. So you see the very clear color in the difference in the color in the vegetation. So you go back 3 weeks later, the ecology, the ecosystem is so dynamic that all of this grows back, but it's younger, it shows a different color, so that's another sign that you know where the salt water went. All right, so in conclusion, this was really the first comprehensive field survey of tsunami impact in the Galapagos Islands. There haven't been people there that long to know about these impacts. It would have been impossible to do without the consent and cooperation of the national park, literally impossible to do. Because you had very dynamic topography and bathymetry, you also have very variable run-up patterns. So you have to come up with some method to direct the survey. You can't just be going around the entire island getting off at every single beach. And so we use numerical models to help us understand where to go. Generally speaking, moderate impacts, but so far it seems like it's a pretty quick recovery. Thank you.
Sorry, I'm a Mac person. Okay, what I will do, I will present to you briefly some of the findings of the International Tsunami Survey Team. The International Tsunami Survey Team is an ad hoc group of scientists. It's been around since the early 90s, and we go after every big or small tsunami to try to document and talk to eyewitnesses, make waterline measurements, find the watermarks. And the kind of things we're interested in is the penetration, the local flow depth, the overland flow depth. By talking to eyewitnesses, the number of waves that were, the polarity of the first wave, where the shoreline withdrew first or whether it advanced, and also what exactly they did, the survivors, of course, after the tsunami or after the earthquake, so that they actually saved themselves. So this is a highly international team, and I'm sure I'm missing some people. This is many more people worked in Japan, but I will present to you some of the main findings of this team. These are some of the people who are not here, and on the left is the senior author, Professor Yalciner, and the other people. Just as a quick reminder, as you well know, Japan is no stranger to large tsunamis. The largest one before this was the 1993 Okusiri tsunami, not really a mega tsunami, but the 869 tsunami, for which we've heard in the very first presentation, was a tsunami that was not entirely well known before this tsunami happened. Hence, it was not used as a design tsunami for the Fukushima nuclear power plant. Even though evidence existed, it was largely not considered in the design. Now, just to give you some of old Japanese photos and woodcuts, these are very similar destruction from the images that we've seen, and I'm not going to show you hundreds of videos or almost no videos. This thing is a slight problem. This is the pattern that you've seen before. We call it, the ones who've been working on this for 20 years, we call this the fingers of God, as it goes out, and it's a classic effect of refraction over topography. This is the, I don't want to spend your time to show you more animations of tsunamis, but this is the impact along the Japan coast. And when we do these field surveys, there are two things we concentrate on. One is the flow depth, the overland flow depth. That's the flooding depth. And if you were in the press conference in the morning, you heard probably how much more important it is to refer to the flooding depth over land versus referring to the tsunami run-up height. And of course, the maximum run-up, which is the most inland penetration point of the wave. Now, to model all this, and why do we want to model this? Where am I getting this? The main interest in this particular presentation is the effect of the breakwaters. Japan had constructed some massive coastal defense measures. Some of them you've seen on the videos. There were seawalls right at the coastline, but there were other defense measures, these offshore breakwaters. One of them in Kamaichi cost about 1.6 billion. It was completed about three years ago. Probably the deepest breakwater on Earth. Close to 60 meters of depth, huge, about 800 meters long, and yet it didn't protect the town. So where this presentation is going is I will show you some of our findings, whether the breakwater worked or not. But to do any kind of modeling, you need an initial condition within, of course, in numerical modeling, you need a representation of the seafloor. How did the seafloor move? And in any event, much more in a very complex event, just like in Japan, there are many different theories and models about the initial seafloor deformation. So in this talk, and at the time that all this was prepared, we had two models available. I'm sure in this conference we'll find out more. We considered two different models for the seafloor deformation, so we will see how well or how badly they work. So here is the answer. It doesn't make a big difference if you're far field. We were very fortunate in this event, and even though NOAA has buoys, the DART system in the middle of the Pacific, there was a tsunami recorded at the Pari buoy, I think this is a GPS buoy, off Kamaishi, and you see the record on the top. And on the bottom, you see two different models, how well they model the buoy. And overall, within the margin of error, both of these source models, what we call initial deformation models, model approximately the tsunami signal. So this gives us confidence that these source models, we can use it to sort of evaluate the coastal impact. Now, I will show you a brief map of the surveyed sites in this survey. Maps, this is, by the way, surveying in Japan was unusually difficult at that time, and it was not just the radioactivity. Imagine that along coastal roads, to cover a distance of about 10 miles, you would spend about 5 hours sometimes. Why? It's not because you had to measure, but to go from point A to point B, you had to backtrack your way up on the mountains and come down because the roads were closed because of debris. So I'll show you some key sites in Taro, and from north moving south. And this is Taro, and the reason that I stayed here is while the Japanese had on the side of the cliffs signs reminding residents of the earlier tsunamis, one in 1933, the other one in 1896. This was even bigger. In Miyako is the site where the famous movie that you've all seen, I mean, there are many videos on YouTube, and at the time of the overtopping of many different ships that go there, and what we do there, and my colleague Hermann Fritz, we work together, showed it in the morning, we go in and we try to find the exactly same point of view that the video is shot, and then we go back and we try to infer the water velocities. We do image rectification, we change the points of view, but we have to have exact measurements. So this is part of what happens in the field survey. This is the video, which I will not show in the interest of time. These are shots from the video, from the movie that was done there and the overtopping, and this is what we do to try to find out velocities, and Professor Fritz spoke about it. But let's talk about Kamaichi, which is where the breakwater was. So, oops. This is the town of Kamaichi. The tsunami entered most of it as a jet, if you will, in this particular location. And this is some of the effects. Now, here is the breakwater. And what's quite interesting about that breakwater, this is the 1.6 billion coastal breakwater. It was controversial to start with, and will still remain controversial. As part of the controversy when it started was that people from Tohoku University estimated that the tsunami might go out and reflect off the breakwaters and impact another area severely, and it ended up that they built this, and then they built another breakwater. Very, very expensive coastal works. So, what is the effect, the punchline? If you look in at different locations, and this is using one of the models, obviously I showed you both models, both source models work about the same, but the importance is comparing apples with apples. So in both of these cases, we use the same model, and this is full inundation measurements of the kind that we saw in the beginning, and we take the breakwater out, and we leave the breakwater in, and as you can see, without the breakwater, of course, the breakwater does have an effect, but it's really a marginal effect. I mean, in most cases, the reduction is of the order of 2 to 3 meters over a flow depth of about 12 meters. Whether that was worth spending 1.6 billion, I mean, it's an open discussion, but it's quite clear that the breakwater did not have the desired effect, if it had any. People have argued that, yes, maybe delayed the arrival of the wave by 6 minutes, and okay, for some people, 14 meters versus 12 meters means the difference between life and death, sure. But at 1.6 billion, I mean, there's much more civil defense measures that you can take. Same thing in Ofunato. By the way, the breakwater in Kamaichi was partially destroyed. In Ofunato, the breakwater was destroyed. So both of these would have to be rebuilt, and there's controversy right now about to rebuild them or not. So this is some of the pictures in Ofunato. Before, after. Now, last point that I will mention is the tsunami forests that were tried in Japan, and a classic example is in Rizikuntacata. Extensive devastation, you see before and after the sand spit is almost gone. There was a tsunami forest exactly because this area is so vulnerable. I think the number is that there were 70,000 trees there. There is only one surviving. Again, there was a standard it was fairly controversial in the tsunami community how effective tsunami forests are. Work that we've done as far back as 1998 with the Papua New Guinea tsunami showed that they're probably not very effective. Then Hermann Fritz and Nick Aligeris, who is here, surveyed places in Solomon Islands and in Java, in South Java in 1996, 2006, and then 2007 and 2009, and clearly showed that tsunamis can overwhelm coastal forests. Of course, it's just a question of size. But in this case, this was way too dramatic. There is not a single, not a single one. There's only one tree, There's only one tree left. So, in summary, what does all this mean? Long, narrow bays amplified the tsunami. One of the things that happened in Japan is pure geometric amplification. These are the places that are not vulnerable to wind waves, so cities and coastal villages and fishing villages are built at the top of the bays that are extremely well protected from wind waves. Unfortunately, it's exactly the places where you get very high amplification of the tsunami because of the narrowing. It's just pure geometry. It's almost like having a bottle. At the most narrow part of the bottle, you have higher velocity. The same thing in open sea like this leads to higher heights. So they were doomed to start with, and they were pretty aware of this, hence the whole idea of the breakwaters. The tsunamis propagated far upstream riverbeds. I didn't have time to talk about this. The coastal forests planted for tsunami protection were completely overwhelmed. I think this will probably settle this question forever. And as far as the tsunami breakwaters, I'm afraid that this will not settle the question forever, but they seem to have offered very, very little protection in the overland flow of the tsunami depths. And even the ones that they were there, and this is not third world design, this is Japanese design, and they were partially, one of them was gone, kaput. The other one was partially destroyed. What worked? Public education and preparedness reduced fatalities. Comparing with Banda Aceh, that some of us here were there and we've been surveying tsunamis for a very, very long time. I mean, if you were, and Professor Borrero, who is here, was the first scientist to enter Banda Aceh 4 days after the event on December the 30th, 2004, the fatality rate in Banda Aceh that resembled, I mean, the scene of the destruction resembled very much Japan, was about 90% dead. In Japan, a rough figure, it varies province by province and city by city, but the number among the coastal residents, I'm talking about the people that were actually in the inundation zone, is about 10%. And Japan had fantastic and extremely good public education efforts, so in our view, this is where to invest and not in really huge and hard structures at multi-billion-dollar cost. Thank you.
Okay, we're going to go ahead and open it up for questions. Does anyone have a question?
Dan Vergano with USA Today. I'm wondering, last speaker, is it clear how high the highest waves got on these inlets where the waves are amplified, or is that still sort of under discussion?
Depends where you were. I mean, anywhere, I mean, maximum has been reported, it's about 40 meters. Typically, but again, this is along the open coast, it's very different, but if you look at the maximum that we know of, is about 40 meters. Maximum in Banda Aceh, 38 or 42 meters. So it was very comparable to what we saw in Indonesia in 2004.
Any other questions? Yes.
James Beal of Freelance. I wonder if you could comment on what is the cause of the doubling of the tsunami in the open ocean. Does that have anything to do with water depth slowing down the advance and piling up behind it? And what are the satellites looking at? Are they measuring the altitude of the sea surface or some optical shadow?
Okay, I think you have two questions. First is for what caused the merging tsunami. That I show one of the slide is topography. Because in the deep ocean, the sea mountain and the ocean ridges are the major features of topography. So when the wave pass through those topography features, so the wave front is nudging and bend into a different kind of direction. Then those after even the front pass these ridges, they still converge each other. Then once the front converge, then the double the tsunami height. That's why the tsunami can travel long distance without losing power. That's why it can cross the ocean and kill people in another side of the ocean. So that's only in few locations because those topographies are known. Once we know the source, we know the collocation of the topography and the tsunami source, then we can predict where a tsunami can hit. Then we can just evacuate the people in those locations. We don't need to have a basin-wide or even global-wide evacuation or panic to the most public. So that's the significance of this study. Another thing you mentioned, the satellite. The satellite is really a lucky case because this thing had been speculated a half centuries, but trying to catch such a phenomena is very difficult because satellite cannot change the orbit. So you have to be at the right location at the right time, then see the merger. You know tsunami travel very fast to see that point. Then you also can measure other points using other satellite to compare the one, see the merger point, with those satellites that didn't see the merger point. They can see how the tsunami height is double. It's clearly confirmed. The many scientists speculation for the last several decades. This is the first time actually we see such a merger phenomena. So that's basically doesn't matter how you model it, you have to see the real case. So that's we think is one of the million chances we see this. We are just lucky to see this.
The answer is the radar satellite measures the radar pulse. So you could measure the topography, the change of the sea level, basically, very accurately to about centimeter or so, several centimeters.
Okay.
I have a question from our webcast. What lessons do the speakers see for the Pacific Northwest?
It's a question to me?
For all of you, what lessons do you see for the West Coast and along Washington and Oregon and British Columbia?
What we know from our study, for example, the Crescent City, that's they often get hit by the tsunami from Japan, also from Alaska. That's because there's an offshore topography that's a ridge far beyond that point. That's why the tsunami always goes that direction, because it's merging tsunami before reaching the Crescent City. So that's many points we know can be hit by tsunami because of the location of that city.
And what about the rest of you? Do you see any other indications of work in the West?
Yeah, okay, I'll take this. I mean, the main lesson for me is the public education and the fact that hard structures don't work. I mean, when you have an event, just like what happened in Japan, a very extreme near-shore event with minimal time to evacuate, I mean, you need to have really good public education. People have to be prepared. They have to know where to evacuate to. The message has to be repeated often. One of the things I didn't have time to say is that even in Japan, if you saw some of these videos, possibly because there had been an earthquake the day before and that had not produced a tsunami, people did not evacuate the way we would like them to. I mean, you could still people in the videos standing around and evacuating in the last minute. That is bad. That's really bad. I mean, probably a lot of these people are not with us anymore. So again, I think the main lesson is, and comparing with Banda Aceh in 2004 and this one, and to the tsunami, Japan 211, is that public education, and both of them are very similar events, very close to shore, massive earthquake, no time to really give a comprehensive tsunami warning. You need to have nothing like emergency, I mean, public education and preparedness. So I think this is what we need to invest in.
Harvey Leifert, freelance. One thing I haven't heard in either of the presentations is some kind of measurement of the actual force of the tsunami. I presume this is related to the event that generated it, but I don't know if it correlates to the height of the wave or to anything else in particular, and I don't even know if it is measured, and if it is measured, in what units. Can you help me?
Let me just take this and then I'll pass it on to Pat. When you talk about the force, you have to see the force on something, on a structure. I mean, the force by itself doesn't, I mean, it's the force, I mean, we'll talk about the force when it hits something. One analogy that I've read somewhere, and it's not mine, is that on the Kamaichi breakwater, it was about 2,000 jumbo jets hitting it at 1,000 miles per hour, or something. I mean, or something ridiculous like this. But it's very hard. It depends on the height and depends on the velocity. I mean, if you have inside the bay, the velocity increases, the height increases. So it's not easy. I mean, you can talk about the tsunami energy, and this is where seismic instruments actually help us estimate and find out how much energy is released, but over the whole seafloor motion as it moves during the earthquake. But to talk about the force, you need to have a specific, if you give us a location, if you give us a structure, we can tell you what the force will be from the model, but we cannot sort of say this before having something specific. Pat?
Yeah, so just say, when you talk about force on a structure, again, it's the velocity, and there are very few instruments out there that measure velocity during an event. So what you can do from an engineering perspective is you can go back and look at structures that were both damaged and structures nearby that were not damaged with some estimate of how high the water was, and from that, you sort of do like a reverse engineering type of thing, and you can figure out what it would have taken to cause that damage. And so that's the type of thing that we're working on now with a lot of the information out of Japan.
Comment, maybe our colleague Emil Okal at the back, Professor Okal.
Came out in 1983 in Japan, and generally speaking, we can say that it's something which the fraction of energy of an earthquake which goes into the tsunami is something which grows with the size of the earthquake, and which is typically on the order of a few percent of the energy of the earthquake itself. So these things are measured, they're measured in units which are ergs or joules, and that can be measured both by a classical approach, which is to compute the displacement of the ocean floor and to see how much energy goes into displacing the water, or it can be computed using the theories of normal modes, and you find about the same results, which is a few percent of the energy of the earthquake.
Thank you. We have time for 2 more questions. Okay, go ahead. I'm sorry.
OKAL. I'm from Northwestern University, and Dr. Song showed one of my figures on which I could have some comments by the way.
Okay.
Thank you.
So,
Great. This is Alex Witze with Science News. I wanted to ask Dr. Sinilakis, I think, or if anyone else wants to respond, was there anything about the mechanism that generated the earthquake, in particular I keep hearing about this overthrust, the movement of the seafloor during the actual rupture that made this tsunami different from other ones you have observed in the past?
I cannot comment on that because I'm not a seismologist. What I do is I get from seismologists, maybe I'll pass the baton to Dr. Okal, who is who can tell us about this, and they give us the seafloor deformation, and we work from there. We take it from where, but this is, unfortunately, it's not my field. Dr. Okal, do you have a comment? Can you?
Well, I could, because including this press conference, I could say that
what was exceptional is that it was so big, and no, we didn't find anything we had seen before because we're too young. And we've been in this business only about 20 years, and perhaps if we had done the work in Chile in 1960, we would have found similar things. Fundamentally, it's the biggest earthquake probably after the main 3. It's somewhat seismically, it's somewhat smaller than Sumatra, but what was remarkable is that there were displacements on the ocean floor which did not scale well with the size of the earthquake, with the magnitude. But the earthquake is a scuffle to some extent, in that it had displacements which reached, in some points, 50 meters or so. And
did you say 50 or 15?
No, 50, 50.
Exactly.
50. Okay? Cadesiat. Which were greater than would be expected even for that large earthquake. So it is a question of violating the scaling laws that we are used to. That plays a role in the near field. In the far field, it plays much less of a role because the far field looks at the big picture, integrates, if you wish, averages over the source area. So, but this is something which was a kind of cold shower to many seismologists, that these scaling laws, you're supposed to tell you how the sources grow with the size of the earthquake were violated.
Last question.
Rich Monastersky from Nature. For Dr. Song, with this constructive interference that was going on, the merging, was that a factor in the near field? And then I guess for Dr. Sinolakis, was there enough time to evacuate from a 40-meter wave?
I like Dr. Song.
Okay, that's a good question. See, for the near field, what we see here is a far field because that's our satellite observation catches that point. For the near field, we didn't see that, but we assume the theory applied to there too. But for a near field, you don't have too much time actually to see this. Then you do the forecast. But you know that's not an issue here. But that same mechanism can work because coastal topography also affect the tsunami merge. Let's see somewhere the tsunami can be 50 meter in this time somewhere in Japan. So there's a very high tsunami. It must be modulated by the topography.
Okay, thank you. Just to piggyback on it, classic refraction theory applies everywhere, but you need sort of large distances to see the effect of ridges, large propagation distance. You're very close. I mean, you're in the deformation area. Now, to answer your question, people could have evacuated. In most places, yes, because there is in Japan they were much luckier than they were in Banda Aceh. And the reason is that you can vertically evacuate. I mean, most of the high-rises, they were reinforced concrete buildings, survived incredibly well. I mean, there was minimal damage, if any, from the earthquake. Even the Fukushima nuclear power plant, I mean, recent results show it was not damaged by the earthquake. So there was the opportunity to vertically evacuate. You could go to the second to the third floor of a building, and in fact, a lot of the videos were shot from there. You didn't have to run 3 or 4 kilometers inland to get to high ground. The people in Aceh, in some ways, were more unlucky because the structures they had collapsed. I mean, the first sort of high-rise structures were, fairly further inland, so there was, it was not easy to evacuate. But if you had, to come back to your question, if you had to run for 4 kilometers to evacuate, unless you were a marathon runner or, a long-distance runner, you would probably not fare very well.
Okay, thank you very much. I'm sure our speakers will be happy to take more questions. We'll have to wrap it up here for the next press conference. Thank you.
USC's press release, it will be on the USC, it should be by now in the AGU site about the results of Dr. Lynette and myself.